Thank you very much. Thank you to Andrea. Can you hear me? Andrea and Francesca for this amazing conference. We are having a great time here, and I'll try to do my best to contribute to its success. So, notes on type truth and consistency assertions. So, a little bit vague as a title, so let's try to make it a little bit more precise. Okay, so I'm talking about axiomatic truth theories, just to be clear about what is the topic of the talk. A particular kind of axiomatic truth theories. These theories, unlike the usual construction, are formulated in a three-sorted language. You have truth and syntax on one side. We will see more about this later, but just let me give you the idea. You have truth and syntax on one hand, and object theory on the other. And this truth theory, this package, this phantom, truth plus syntax, applies to the object theories. We will see what this gives us. Okay, the motivation for studying these theories was mainly philosophical. We wanted to understand arguments that try to write a philosophical story, extract a philosophical story out of axiomatic truth results. And also, we wanted to somewhat formalize informal meta-theoretic discussion in which numbers and expressions are somewhat always distinct and not identified as in the usual practice of working in formal systems. Also historical, because this setting really captures Pascal's original picture of the method theory in his seminal paper on truth theories. Also, so what I want to do now is just to relate these theories to more natural mathematical theories, such as standard arithmetical systems, particularly weak arithmetical systems, and principles. Also, we have another motivation. We want to try to write also a philosophical story and try to see whether we can, these results can tell us something about the notion of truth or in general. Okay, so let me give you just a definition of the theory. As I told you, just three-sorted language. We have an object theory, we have a syntax theory together with truth axioms. And that's it. Briefly skim through the axioms. So we have axioms of an arbitrary object theory U. We'll see the assumptions on U later. We have a theory of syntax which is actually bus S12, and we will see what it is later, but it's a theory in bounded arithmetic which is minimal in a good sense. And also we have, and it's just right for developing syntax in a good way. And also we have a theory of sequences, which is just a theory that is needed to bridge the syntactic and the mathematical domain. And it's just simple, it just says that sequences are non-empty, and given a sequence, we just tweak one element at a time. And then we have classical Tarski-style compositional axioms for satisfaction in this sense, because when you have two domains, it's tough to the axiomatic truth. Okay, so what we do in this talk, we just prove this. Let U be finitely axiomatized, or as we shall see, we can relax this condition. A consistency statement, an intentional consistency statement for U is the unique pi1 second sigma modulo provable equivalence in unique modulo provable equivalence in either plastic pronunciation, such that TU, the theory of truth applied to U, is mutually interpretable with Q plus sigma. So if we take this expression as an equation with sigma, the variable, con U, an intentional consistency statement, is the unique solution to this equation. And we can extend it to for reasons of time, I just focus on the finitely axiomatized case. And I give you just little hints on how we deal with the infinitely axiomatized or arbitrary case. But yeah, the techniques are basically the same. So keep in mind that I talk about finitely axiomatized theories, but we can extend it. Okay, we're not at the beginning. I put the table of comes a little bit later, so don't worry about the on time. So preliminary is some technical notions, including the formalization of Hanking's completeness proof in weak arithmetic, the so-called Hanking-Pfefferman construction. Weak arithmetic, I mean really interpretable in Q. Then we tackled the result. We first proved one direction. Truth theory interprets Q plus consistency statement for U, and then the other direction, how Q plus con U can give us the theory of truth. And then I conclude with two applications. One is another examples among the many already known between reductions between truth axioms and set existence axioms, predicative comprehension in particular. And the second, try to see whether this result can characterize truth governed by compositional axioms, as opposed, for instance, to this quotation. Okay. Base theory, an important theory, Bus S12. This theory will be taken to be interpretably any object theory that we will consider, and also, as we have seen already, it is our theory of syntax. So I don't go into the details, but just by looking at what fact one says, we can get a grip of what this theory is about. So it just extends its language extends the language of arithmetic, and I really don't want to go into the definition of the symbols. But okay, let's just say that this theory was studied by Sam Bass in his PhD dissertation to study p-time computability. And so in fact, probably total functions in S12 are exactly the p-time computable functions. In particular, an important role is played by the smash function, gate. This is a function that has polynomial growth rate. And so this gives us many insight of why this theory has some nice features also in formalizing the syntax. But we'll come to that, back to that. More importantly, S12 is finitely axiomatizable. S12 is interpretable in Q on a downward closed cut, and we'll see what that means. And also, very importantly, an intentional arithmetization of the syntax can be carried out in a natural way in S12. Namely, we know when we do arithmetization in a nice way, namely by defining formulas in some theory and proving their properties, not appealing to a priori arguments like representability of recursive functions. A natural system in which we can do that is I sigma 1, for instance, because we want syntactic notions to be captured by sequences that encode their construction. So there exists a sequence that has some nice properties. I sigma 1 has induction for dealing with these definitions. And so we have nice representation of intentional formalization of the syntax. Now, when we don't have sigma 1 induction, when we don't have this kind of induction, it's more difficult. But sigma 1, 2, S12, it's really nice for this, because this match function gives us the possibility, since it has polynomial growth rate, gives us the possibility of bounding these sequences by polynomials. So, okay, we don't have sigma 1 induction, we can do the same thing. So there exists a sequence that encodes the construction sequence for a term, for instance. And we can bound those sequences, so everything is natural. So that's why I chose S12 as the theory syntax. Also because it's interpretable in Q. Okay, very important detail, the method of cuts. So cuts are initial segments, and the formula phi is inductive in T extending Q if and only if it satisfies the premises of the induction axiom. Moreover, it is a cut, T-cut, if T proves that it defines an initial segment. So an important lemma that we will extensively use is the following. Whenever a theory proves that some formula, theory extending Q again, proves that a formula is inductive, we can shorten it to a cut. just by restricting our attention to the initial segment that it defines. More importantly, this cut can be taken, always be taken to be closed under addition, multiplication, this match function, and satisfy the axioms of S1, 2. And this is just by reasoning, take the definition of an inductive of a cut, it's closed under successor, and so you close it under addition. Close under addition, you close it under multiplication, and so on. Very important. So interpretations. So yeah, I don't want to contradict the speaker that came before me, but proof theory has also, it's not only cut elimination and normalization, but it's also interpretation. So there is structural proof theory and interpretation of proof theory. And interpretation of proof theory is somewhat semantically motivated, and it's meant to just find relative interpretations between theories. So we write a triangle notation, which is similar to the notation of the previous talk, to say, so we write V triangle U for there is a relative interpretation of U in V. Also, we will employ, we have said that all theories that we consider are interpret S1, 2, and also that they are formulated, for simplicity, we take them as formulated in a relational language. Okay, so we have another important piece of the puzzle is Wilke's characterization of the pi1 consequences of pi delta 0 plus exponentiation as those pi1 sentences that are interpretable in Q. And this characterization gives us the following. If for any pi1 sentence sigma and sigma prime, if Q plus sigma interprets Q plus sigma prime, Q plus sigma interprets Q plus sigma prime, if and only if I delta 0 proves that sigma implies. Also, this will be used at the end of our talk. Also, the following will be used at the end. And this is a beautiful strengthening of the completeness theorem, which is not really known among philosophers, especially. So we know that Feynman improved somewhat the completeness theorem by saying that a theory does not interpret its consistency statement, intentional consistency statement plus PA. We can do much better. So Padlock's result is really that Q does not interpret Q plus its consistency statement. If, Q is defined with sigma 1 formula. And this is nice because it's really close to the theoretical lower bound in a sense. It's almost optimal. You can never know whether something is optimal, but this is nice. Okay. Last piece of the puzzle before tackling the result. Hankin-Feynman construction. For any U, S1, 2 plus con U interprets U. This is really just the formalization of Hankin's completeness proof. But you do that, and this also Feynman did it in the 60s already for PA as a theory of syntax that you can add to your consistency statement. But now, this is also, I think, Pudlak's result. You can do that with Q. And of course, Feynman's result employed delta 2 induction, and here you can do it with much less by using the method of shortening of cuts that we have introduced before. So what you do, take the completeness theorem proof. We can phrase it as the search for the leftmost consistent path of the full binary tree, consistent with the completion of the object theory. So you have this path here. So how do you prove the existence of this path? In the standard case, the formalization of completeness theorem, you use delta 2 induction. Of course, here, in our ambient theory, S1, 2 plus con U, we have no such induction. So what we do is just we use definable cuts to show that we have the existence of this path, and also the numbers that are defined here are course, are taken to define a model. And the model comes with a truth predicate. The truth predicate satisfies compositionality, full compositionality for all sentences in this card that defines the leftmost consistent path of this binary tree. Also, we have, more importantly, we have reflection for sentences in the card with relation to this truth predicate. So, if X is a sentence and this in the card and is provable in U, sentence of the ground language, the base language U, it is an extension of the truth predicate in the sense of this construction. We will see that this truth predicate will play an important role. Okay, so we just tackle the result. First, we have the theory of truth, with this entangled syntax, this three sort of theory, functor, truth, plus syntax that applies to object theory on one hand. We want to get an interpretation of Q plus con U in the theory of truth. And this is proposition one. Let's forget about the lemma G, which is just a strengthening, immediate strengthening. So, if you strength axiomatized, TU interprets Q plus con U. If you schematic, TU interprets TU plus all instances of the schemata of U are true, interprets Q plus con U. Let's consider the fancy axiomatized case. How do we obtain the interpretation? Again, we use a method of shortening the cards and prove lemma 4. We just prove the consistency of the object theory on a card in the theory of truth. And this card, so consistency statement is relativized to the card, and then will give us the domain for the interpretation. Okay, how do that? As usual, in task is trivial consistency proof, semantic consistency proof. All axioms of the base theory are true, all instances preserve truth, all theorems are true. Small problem, we don't have induction to do that. So, again, we restrict our attention to a definable cut in our theory of truth. And we prove this lemma, this reflection lemma, all theorems of the object theory are true, relativized to this cut, to a suitable cut. And one gives you a hint of what we do. We just show that given a proof whose elements are in the cut we have isolated, then its last element is true in the sense of our truth predicate, of the theory of truth with this entangled syntax. So to establish something like this, we need to show that this is inductive. So holds for 0 when the proof has no length. If holds for a proof of length n, then we prove it for, we assume that the proof has length n, and we prove it for n plus 1. And to do that, we need to prove that this cut k that I have put into the equation, into the expression, has to have some nice properties, like behave in a nice way with syntax, and there is a lot of work, tedious work on you need to be sure that it can be proved. But the idea is really that you prove reflection relativized to this cut, defined in the cut. And once you do that, you're okay. So you will have one direction. The theory of truth interprets Q plus con U. Okay, how we get the other? The other is just to, for the other direction, the basic idea is that we employ the Hankin-Fefferman construction as we have defined it a little bit earlier. So this Hankin-Fefferman construction, remember, was just a formalization of the Hankin's completeness theorem for U in this weak arithmetic plus the consistency statement for U, and came with a truth predicate. Now, this truth predicate is of no use for reasons that we may discuss later. No use if you want to interpret a full truth predicate, the one that we employ for PA class, full satisfaction class, those kind of theories. This truth predicate is of no use. But in this setting, with this theory that plays really the role of truth truth axioms are independent from the object theory. The object theory does not give anything to truth axioms. In this setting, when we have this kind of truth predicate, this construction is really useful. In fact, what is the proof idea? The proof idea is simply interpret the truth predicate as the truth predicate given in the Henkin-FilMat construction. A little bit more in detail, we just relativize quantifiers of the object theory to the domain of Henkin constant in the sense of the arithmetized model that we have constructed. We relativize syntactic quantifiers to the cut I. There was, remember, the cut that gave us the existence of the leftmost consistent part, those numbers here. Sequential quantifiers are just, or sequences of assignments, remember, they are just relativized to sequences of elements of the domain of Henkin constants. Again, I mean, relations and homological constants of the object theory U are just interpreted as the Henkin-FilMat construction tell us. Syntactic constants are not just mapped in the identical fashion. The truth predicate is interpreted as the truth predicate of the Henkin-FilMat construction. And of course, I mean, you have some other logical symbols that are just not important now. So, important thing, truth predicate gets mapped to the truth predicate of the Henkin-FilMat construction. Okay, so we have the other direction. So they are mutually interpretable. Truth theory, Q plus con U, they are mutually interpretable. Of course, here we deal also with a case in which we have U arbitrarily, so U in this can contain a finite number of axioms of schemata. And of course, I mean, here we just noticed that this construction that we have outlined at the beginning, the Henkin-FilMat construction, also satisfies reflection. That is, for any sentence in the cut, if it's provable, then it is in the extension of the truth predicate given by the Henkin-FilMat construction. And this also gives us the possibility of interpreting the claim that both instances of the schemata of the object theory are true in the sense of our theory of truth. Okay, so it seems that we have what we wanted. Of course, I mean, there are many details here, and especially working in these weak theories is so tedious, but I just wanted to give you the idea of how things are done. Yeah. And so, yeah, please forgive me if you feel a little bit lost. Okay, summing up, I mean, we're back from where we started. What we have achieved, it seems, is that if U is finitely axiomatized, then con U, an intentional consistency statement for U, is the unique pi1 sentence sigma modulo provable equivalence in either plus 0 plus exponentiation, such that Q is movement interpretable Q plus sigma. How we did that? We just applied Wilke's lemma. So we have the mutual interpretability of the two, and then we just said, replied the lemma that says that Q plus sigma, if sigma and sigma prime are pi1 sentences, Q plus sigma interprets Q plus sigma prime if and only if either of these view proves that sigma implies sigma prime. So combining the mutual interpretability result with Wilke's characterization of the pi1 consequences of either of 0, we get this. And we get this in the case in which U is finitely axiomatized, in the case in which U is arbitrary. So really here means finitely many axioms plus a finite set of schemata. Because there are theories like PRA that are infinitely axiomatized, regardless schemata that there are, so it's more complicated. Okay, so two applications. First, we wanted to have another reduction between, if we want to say it in an uncautious way, semantic equivalent or mutual reduction between semantic commitments and ontological commitments, but let's say just truth axioms and elementary comprehension and predicate comprehension. So we have the functor that applies truth plus syntax to an arbitrary object theory. So we now consider another function, another functor. This functor applies predicative comprehension to an arbitrary object theory. And it does it in a very usual way. We just use relativizing predicates instead of using sorts. So predicates for objects and classes. We just relativize all the axioms of the object theory to the sort object. We have a predicate that expresses membership. And we just apply predicative comprehension in the most natural way. And the phi, I mean, the formula phi that to which comprehension is applied, the only condition we put on it is that all the variables have some sort. So for each variable, there is a function that tells us for each variable in the formula to which sort it belongs. Okay, so again, I mean, just the idea that you have an object theory applied to predicative comprehension. And it turns out that these two functors, truth and predicative comprehension, really are closely tied. So, by result of Albert Visser, from which I borrowed many of the techniques that we have, that I've used to prove the mutual interpretability result, we have that predicative comprehension over U is mutually interpretable with Q plus coin. So we just combine the results. And we have that, basically we have that predicative comprehension over U is mutually interpretable with truth over U. Also, we can apply again the Wilkes result to get this nice characterization of the consistency statement. And this consistency statement, I mean, this is not an equation anymore, just an expression, but again, predicative comprehension for U, Q plus sigma Tu related by mutual interpretability. The unique solution to this weird equation is the consistency statement. Okay, again, this holds also for the more general case of schematically axiomatized theories. Okay, last slide. Does this tell us something about the notion of truth as axiomatized by compositional axioms? Okay, so if you take these theories as, so one motivation for studying these theories was, let's see what truth axioms do without any interaction with the object theory. So the motivation is really that sometimes, I mean, there are axiomatic theories of truth, you prove things, but schemata of the object theory interact with the notion of truth, and you don't know what is playing a role. So are there mathematical assumptions playing a role? Are there truth theoretic assumptions playing a role in some arguments? So one of the motivations for disentangling was really this, to see the truth axioms as in their pure nature, which has some syntactic aspects, of course. Truth is always coming with some syntactic assumptions, some ontological expressions, but no interaction with the object theory. Okay, so it seems that actually, I mean, also recently in the usual entangled setting, it's not clear. I mean, there are many proposals that try to equate or try to extract compositionality from this quotation. So T phi, if and only phi, may be allowing parameters. There are many, especially allowing parameters, but there are many attempts of doing this. And some of them are also successful. So what we try to argue here is that if you disentangle things, if you focus on the pure truth theoretic nature of these axioms, either compositional or disputation. You see that for compositional axioms, you have some characterization. These axioms are equivalent, modulo mutual interpretability, to a consistency statement. So a statement of meta-mathematical nature which is not reachable, which is out of reach of the object theory, either in the sense of course, probability, or in the sense of interpretability for Putlar's result. On the other hand, all that we have said, and let me go back here. I didn't mention this because I didn't have time, but it is not difficult to prove that if we formulate the theory of truth only with disputation axioms, disputational truth axioms, defined with unverified Lang parameters, then this result does not prove true. So it seems that also we have not only a characterization of compositionality, composition of tasking style axioms as statement of meta-mathematical nature, consistency statement, not reducible to the object theory, but also we have an asymmetry between compositionality and disputation, which is somewhat also relevant to the recent debate. Thanks.
Questions? Yes, over here. Either one of you two.
It is well known that when you go to stronger, much stronger systems, this sort of correspondence breaks down. Okay, for instance,
which one?
I mean the correspondence between the possibility of giving a compositional definition of truth and consistency statements. For instance, most basic case is Gödel-Bernays set theory with respect to CF. And where is the limit, the boundary, and is there a principal reason to see where exactly things break down?
I think things break down immediately. So, because you just have this characterization there, at that level. Oh, sorry, I forgot. This theory of truth is conservative over U. So the functor that applies to U does not give us any new theorems in the language of U, because any model of U can be expanded to a model of TU, just a simple argument. So really strong notion of conservativity. So breaks down immediately. So what is good? But of course your question is good because we want to have, to fully accomplish this project, it seems we need to argue that these compositional axioms are, in a sense, minimal. So all other compositional axiomatizations of the truth predicate kind of contain this set of axioms. If we can do that, then we can show, okay, forget about what you can get. I mean, of course you can go much stronger, but at least if you give it some compositional axiomatization, then it has to be at least out of reach of the object theory. And that's already, I'm already happy with it. Of course you're right. If you go on, I mean, there's no such correspondence, but one side of the correspondence, namely Q plus connu interpretable in all these theories, I mean, that's already something that I look forward to.
Does your framework lend itself to some iteration, thinking of your TU construction? And if so, how does it relate to FilMat's idea of progression, unfolding system?
This is totally unclear. So just what I have studied recently, for a few years, and this theory is kind of new. Richard Hack had the idea, and also Volker Halber had the idea, and I worked on these theories. So we're trying to understand how it would be possible to make iterations, so typed iterations, so different truth predicates, and also type free. I have no idea how this can be done, because it's really difficult, because you see there are three domains here, And if you go to another level, then you have to build up another theory of syntax. But then you want to argue that the syntax is somewhat universal, as Leon points out. And so it's very, but I still have hope, at least for the iteration, to do that in a way that can be also justified. But yeah, of course, I have no idea how to do that.
Any other questions? It's very rich talk. That being the case, let's thank our speaker and